Moving on in Chapter 9, we're going to discuss the sampling distribution for means in this video. In the previous video, we discussed that sample means are going to be used to infer about the population mean, but we do need a sufficiently large sample size. If a sample mean is close to the population mean, we can say that it's accurate and that it has little bias. The sampling distribution is an important concept that we've already discussed back in Chapter 7 and Chapter 8. We're going to alter that slightly for means in Chapter 9. Recall that the sampling distribution is considered to be a dot plot or a histogram of all possible sample means that would result from drawing repeated samples from the population. So it's taking sample after sample after sample from the population, placing those sample results on a dot plot or a histogram. Back in Chapter 7 and 8, we used the central limit theorem to see if our sampling distribution would be approximately normal. A dot plot may be something like this, where we could draw a nice bell-shaped curve over our data. So all of these mini samples made up the sampling distribution. And the same thing applies to means. Now, what we want to do is use the unbiased estimator. And I can see here that word got cut off. But we want to use the unbiased estimator to make an assertion about the population. The mean of the sampling distribution, this value right here in the middle, if it's normal, should have the same value as the population mean, which is mu. And that is known as the unbiased estimator. So it's taking each sample, each mean from those samples, and averaging all those many means together. That's going to give you the unbiased estimator. That should allow you to infer about mu. Taking the x bar from this sample, the x bar from this sample, the x bar from this sample, all the way through the sampling distribution, finding the mean of those means, that will give you the unbiased estimator. To clarify this, let's look a little bit at example 1 here in the notes. A biologist is studying the effects of a particular non-organic fertilizer and the effect that it has on the population of a certain type of fish. He collects 18 fish and finds that they have a mean weight of 1.3 pounds. Assuming that the sample of 18 fish is random, he concludes that the sample mean is an unbiased estimator. Therefore, the mean weight for the population is also 1.3 pounds. We want to know, why is this an incorrect interpretation of the unbiased estimator? All right. Well, as we just defined, the unbiased estimator is not just one sample mean, but it's the average of many sample means. So the first sample mean was 1.3, but we know samples vary. The next 18 fish he collects might have an average weight of 1.7 pounds. Then the third random sample of 18 fish might be averaging 1.9 pounds as their weight. We would take sample after sample after sample and average all of those sample means together to get our unbiased estimator. So this is an incorrect interpretation because this uses only one sample. And we need many samples in order to find the unbiased estimator. Just a quick note, the sample size was 18 fish. That may seem a bit small to you. From the previous chapter, we had to have at least 10 successes and 10 failures. But that sample size rule changes just a bit with means, as we'll see in the next videos. Moving on to the standard error. Recall that the standard error is the standard deviation of the sampling distribution. Measures the precision of the estimator. If we have a sampling distribution and it is approximately normal, with mu in the middle, instead of using the standard deviation with a sampling distribution, we'd use the standard error. So if you go up a standard error and down a standard error, you should capture about 68% of your samples. Then you could go up 2 standard errors and down 2 standard errors. That should be about 95% of your samples based off the empirical rule. And back in chapter 7, the standard error for proportions was the square root of p 1 minus p all over n. For the estimated standard error, we used p hats if we didn't have p. In chapter 9, for our means, the standard error is found with a much simpler formula. It's sigma, which is the population standard deviation, over the square root of n, where just like before, n is the sample size. It's your population standard deviation divided by n, the sample size. And if you want to find the estimated standard error, that's when you don't have sigma, the population standard deviation. You could use S, the sample standard deviation divided by n. And we'll end up doing this more often than not. So we're going from this square root of p, 1 minus p over n, to this sigma over the square root of n. And you'll need to know these formulas for the final exam over chapters 1 through 9. These will not be given, but you'll need to know those. To wrap up this video and to put standard error into context, let's look at example 2. It says the income in the area in California known as Silicon Valley has a population mean mu of $46,000 and a population standard deviation sigma of 4,500. This distribution is right skewed. It is not bell-shaped. But suppose we take a random sample of 100 people who live in Silicon Valley. What is the expected value of the sample mean? That's x bar. And the standard error. So the population mean of everyone's salary, everyone's income in this area is $46,000. So if I apply appropriate sampling methods, if I have a random sample, which I do, and have a clear, concise question that can help avoid bias, I should get close to $46,000 as an average, as a sample mean every time. Sometimes my sample might be a little bit low. Sometimes it might be a little bit high. Maybe it's $47,000 as the average, but it should be right around $46,000. So I would expect X value, if I had to pick one number, to be $46,000. If my methods are done correctly, then my sample mean should match the population mean. It should be pretty close. So I'm going to expect that these methods are taken into account and our sample mean gets close to our population mean. As far as our standard error goes, I can see from up above my standard error has the form sigma over the square root of n. Well, I know sigma is 4,500. I can divide that by the square root of n. The sample size I know is 100. You can type this into your calculator all at one time. 4,500 divided by the square root of 100, or that's just 10. Either way, you'll get $450. All right. This tells me that not every sample is going to be exactly $46,000 as the sample mean. Some could be a little bit higher, some could be a little bit lower. Well, how much higher, how much lower should the typical sample be? It's not that far away. Typical sample should be within $450 of $46,000. So I could add $450, so it could be $46,450. I could subtract $450, it would be $45,550. But most of my samples most of my X bars will be in this range. I would expect $46,000 as the sample mean. Not every sample mean will be $46,000. Most will be between $45,550, which I got by subtracting these two, and $46,450, which I got by adding these two.